So I've decided to make a linear algebra playlist now. Really just intro linear algebra, more application-based linear algebra. So not pure math linear algebra. This is not going to be a focus really on linear operators. We will cover linear operators, but it won't be the extensive focus of this. Really the point of these videos is more than anything is to just act as a sort of help or tutor for my sister who needs to take a linear algebra course, and she wasn't a math major. She got her degree in biochemistry, so she only went up to Calc 3, and I guess for anybody that's interested in learning linear algebra, I think these videos might be good, but it will be really introductory linear algebra, so questions that you might have regarding linear operators and transformations, different matrix factorizations might be covered in other videos. But I think the aim of this is to make these videos fairly shorter, so not spend so much time talking about the theory and really just talking about how to do the problems, because the people that I'm making this video for, they don't really have to be concerned about the theory of it. They just need to know how to do the problems. But I've sort of outlined some topics in an order that I think would be good, that I think might follow a standard syllabus for a course like this. And so I guess we'll start with what the motivation is for this course as far as linear algebra in general, and then the order of topics. So I guess let's go over the order of topics first. So if I'm lucky, this should be around 13 videos long, but I might end up just shoving topics into one video because they might be closely related. And I'd like to keep the video short, but some topics might take longer than others to make, so some videos might be short, some might be long. I'm not going to make two parts for videos though. I'm not going to make like a two-parter for a certain topic. I'll probably just shove it all into the same video, and that video will just be longer than the others. Alright though, so I think I'm just going to start right off the bat with systems of linear equations and matrices. Now I know all you pure math nerds out there are probably wishing I just started with linear operators, but again, that isn't the point of this course, and really linear operators are not going to be a big part of this course. We will talk about linear operators though, and transition matrices, etc. Then I guess we'll talk about Gaussian elimination and reduced echelon form. Then I'll go over vectors and Rn. So properties of vectors, addition, multiplication. This might include Cauchy-Schwarz, maybe. Then I'll talk about a little bit about linear independence and dependence, as well as basis and dimension, so how to find a basis of vectors. Then I think we can go straight into matrix operations, so this would just primarily be addition and multiplication. So what happens when you add matrices, and how do you multiply matrices? When can you multiply matrices? When can you not? Commutivity, stuff like that. Then I'll talk a little bit about linear transformations and matrix representations of transformations. Then I won't spend too much time on it, but I will mention determinants, just mainly with cofactor expansion, I guess, and then like simple 2x2 and 3x3 matrices, as well as I'll go over inverses. So we won't be talking about things like generalized inverses. That'll be out of the scope of this course. We'll talk about the inverse of a 2x2 matrix, obviously with the formula, as well as how to generally find an inverse using the method of Gaussian elimination to try to reduce to the identity matrix. I'll then talk about eigenvalues and eigenvectors, again at a basic level, just how to find the characteristic polynomial and solve it. We don't need to talk about spectral representation or anything like that. Then I'll go a little bit over inner product spaces, so the dot product and orthogonality. Inner product, maybe I'll talk about outer product a little bit. And orthogonality will lead really into Gram-Schmidt and QR later. Then I'll mention least squares, so we'll talk about the normal equations, how to find a least square solution to a system. Then I'll talk about the 4 fundamental subspaces of a matrix. And then we'll talk about the eigenvalue decomposition. Well, I hope that... So I'd like to hopefully have everything move towards the singular value decomposition. I think that for an applied linear algebra course, the singular value decomposition should be like the end goal, because I think it really encapsulates everything that's learned in like an intro linear algebra course. You can use it to find the 4 fundamental subspaces. It's a matrix factorization, it involves matrix operations, involves everything, and it's a very general decomposition. And then the eigenvalue decomposition is before that. I think I'm just going to do this to sort of lead into the singular value decomposition, because really the eigenvalue decomposition is like a special case, if you will, where we are dealing with square matrices that have eigenvalues. Also, I didn't mention it, but I am going to talk about the OU decomposition. I think I'll talk about that in matrix operations, because the OU decomposition will only involve Gaussian elimination. And then in that, I'll talk about like types of matrices. So this is just a general outline, but you'll probably see on the videos that these might include other things that are written down here that sort of relate to it. But anyway, what is the actual motivation for this course, or an intro linear algebra course? Well, really, it's all about solving linear systems, specifically solving AX equals B. Literally all of linear algebra pretty much revolves around this. Some matrix A times a vector X, all set equal to another vector B. And if we can solve this system, we can find out things around image processing, reaction modeling, signal processing, chemistry reactions. Pretty much everything can be boiled down into a linear algebra problem. And it really is. When you go higher up in numerical linear algebra, you realize that everything is just finding a way to become a linear algebra problem, from partial differential equations to other dynamical systems, everything. And so knowing the basic methods of how to solve AX equals B, which we'll go over pretty much in this course, comes in very handy. So what is linear algebra, though, I guess generally speaking? So linear algebra really is just the study of vectors, matrices, and then systems of linear equations. And in this course, you can think of matrices really just in this application sense of taking systems of linear equations and then representing them as matrices. But I will mention that it is bad to think of matrices as just a block of numbers. I think when I took intralinear algebra a while ago, when I was that was like the first math class where I really had to do proofs, matrices were kind of confusing because I didn't understand this relationship between linear operators and matrices. But really, matrices are not just blocks of numbers. They instead encapsulate what we call linear operators, or linear transformations, or functions, broadly speaking. They are all essentially one and the same. And we'll talk a little bit about that in this course. But it's fine at this level to just say, okay, here's a linear equation, and I can take the coefficients and put it in a matrix, and this is how I represent it, etc., etc. So, as I mentioned, the big goal of this course is really just to solve AX equals B. We want to deal with this the whole time, and sometimes we might want to just solve for X, sometimes we might want to find B, sometimes we're given both, sometimes we're only given B. There's a bunch of different cases, and as we'll find out later, depending on what kind of matrix you have, A, it can be very easy or very difficult to solve this equation. And so we'll look at things like matrix factorizations and Gaussian elimination and reduced echelon form. Basically things that involve more work but ultimately lead us back to the goal of solving ax equals b. That really is a big idea. Every matrix factorization you will see is just going to be a way to help us solve ax equals b. Alright, so I think this first video will just be a basic introduction to systems of linear equations as far as the actual content goes, and then how to represent them as matrices. So what is a system of linear equations? Well, if you're looking at a linear algebra course, you've probably already taken high school algebra. So in high school algebra, you might remember we can have a system of equations. So I'll say 2x plus y equals 5 and negative x plus 3y equals 4. So this is a system. It's a system because we have more than one, so one equation, two equations. And what we did in high school algebra is we would solve for x and y. And so there are a few ways to do this. We could either do substitution, or we can multiply by constant coefficients to try to simplify one expression. But say at the beginning here, I want to first solve for y, because I see that y is on its own. So let's just do what we did in high school. So I'm just going to solve this. I'm going to find x and y. So we have 2x plus y equals 5. So we can isolate y, and that would become 5 minus 2x. Okay, now we have an expression for y, but we need to know what x is before we can get a value for y. So let's take our expression here, negative x plus 3y equals 4, and we'll make this whole equation be in terms of x by replacing this y with this expression we got here. So we'll have negative x plus 3 times 5 minus 2x equals 4. We can simplify, so minus x plus 15 minus 6x equals 4. Negative x, negative 6x gives us negative 7x. And then we'll subtract 15 from 4. That'll give us negative 11. And we could divide by negative 7, so we get x equals positive 11 over 7. So this is one of our solutions. So we have a solution for this system at x equals 11 over 7. So now that we have a value for x, we can solve for y. So we get y equals 5 minus 2 times 11 over 7. So what, that'll be 5 minus 22 over 7. We could simplify a little bit, get a common denominator, so we'll get 35 minus 22 over 7. That's 13. So y equals 13 over 7. Alright, so we found a solution for both x and y, and we would know this works. Obviously we can plug 11 over 7 back into this top equation, and it would give us this value for y, or vice versa. And we can do this with two equations like this, or we could add a third or a fourth or a fifth. And this method is fine as it is, just doing the high school way where we, substitute, multiply by coefficient, etc., etc. But imagine this is 5 equations instead of 2. Well, it'll get very tedious. You'd have 5 equations to keep track of, and it's not necessarily implied that you have a unique solution. In this case, we get a nice solution of x and y, but it is the case that we could have infinitely many solutions, which probably isn't something that you covered in a high school course. In a high school course, all the systems you were given have unique solutions, but we can't always guarantee unique solution. We might have infinitely many solutions, or we might have no solutions available. So what I'm leading into now is how we represent these systems of equations as matrices, and by representing them as matrices, we can do things with them, which we'll talk about in another video, that will make doing that process, finding a solution for x and y or whatever variables, easier. So we had the equations 2x plus y being equal to 5, and then minus x plus 3y equals to 4. And so if we want to represent this as a matrix, it's pretty simple. So we take the coefficients of all the variables, so that'd be 2, 1 in this case, -1, and +3, and that's what our matrix becomes. So we have 2, 1, -1, 3. So our matrix is just the coefficient of our variables in our equation. And just for future reference, I like to write my matrices like this with these brackets, but some people write their matrices like this, so your professor might do it like this. They are both the same thing. However, these are not the same thing. We'll talk about that later. But I'm just going to use parentheses from here on out. But this and this, exact same thing in this case. I know that this and this means something different in calculus with continuity, but don't worry about that in this case. These are just parentheses for my matrices. Okay, that was a weird tangent, but so we filled our matrix, which we'll call A. So I'll label this A. And also for notation wise, I'll make this red. When we letter matrices, when we label them, we generally always use capital letters. So either just the capital alphabet or even Greek alphabet. We could name a matrix lambda, which we'll see later, but it'll be capital lambda. So we always just use capital letters. That's just generally the convention. But there is nothing stopping you. But usually we reserve lowercase for vectors, like we'll see now. So we have our matrix with our coefficients, but we still have our actual variables. And we also have these values on this side that our equation's equal to. So these variables are just, well, they're just that, they're variables. They're not dependent on anything in this case. So we just call this our general vector x. And the size of this vector is just dependent on how many variables we have. So we only have 2 variables, x and y. So our vector x is just components x and y. Simple enough. And this is what we call x in this case. So we've almost formed ax equals b. So now we form b. So b is, in this case, our solution vector. And so we actually know what the solutions are in this case for these general equations. It's 5 and 4. This first equation is equal to 5. So we fill that out, and then 4. And this is our b. So we've now represented a system of linear equations as what we call a 2 by 2 matrix in this case, because it's 2 columns high and 2 rows wide. So if we had 3 equations, this would become a 3 by 3 matrix. So 3 columns high and 3 rows wide. Or sorry, 3 rows high, 3 columns wide. All right. So I think the last thing I want to talk about before I just end the video is really just types of solutions to equations. Now, this gets a lot more rigorous when we'll deal with things like linear independence of vectors and the linear independence of columns of a matrix and stuff like that. But there's generally 3 rules of thumb for if a system has a solution or not. So what we call an overdetermined system, so say overdetermined, is when we have more equations than variables. So that would mean that we had, say, 3 equations here, but we still were only looking at variables x and y. So in that case, we would have a 3 by 2 matrix. So 3 equations, 2 variables. And this is what we call an overdetermined system. And generally, this is often inconsistent and means generally that there's no solution. So I'll write this, I'll write this with an asterisk, because it can be solvable. We can solve overdetermined systems, as we'll see a little later. But at this level, we can think of overdetermined systems as having no solution. And then the inverse is an underdetermined system. So underdetermined. And this would be the opposite of that. This would be where we have a single solution. Or sorry, this is where instead of no solution, we might have infinitely many solutions, or what we'll call a general solution, which we'll see later when we talk about reduced echelon form. And so this would mean that we have less equations than variables. So if we remained here with these two equations, but I added a variable z instead, we'd have 3 variables, 2 equations, so that would give us a 2 by 3 matrix, which would be, again, a rectangular matrix is what we would call it. And this generally has infinitely many solutions. Again, the y in that you don't have to worry about right now, but we'll see it later on. So we'll say, let's see here, infinitely many solutions. And then the last case is just when we have a unique solution. And so this just arises naturally, generally with square matrices. And the way we can think of solutions actually for these systems of equations, since we're dealing with linear equations, if we were to graph these, we just get straight lines the whole time. So say we had an equation like this, and then we had one like this. So if they had a unique solution, this does have a unique solution, it would be here, where they intersect. That would be the best geometric way to think about it. And you could have this for many solutions. We could have freaking 3, 5, 4, 10, 100, whatever. If they all intersected at one point, I know my drawing is not exact, then that system would have a unique solution. And that's what we want. That's the ideal case. It's nice to have unique solutions. But generally, we have infinitely many solutions or no solutions, which is why we have to use other methods rather than just this, which we call back substitution, which I will mention real quick. If you were to, example, start with a matrix like this and put it back into its equation form and then solve it like this, that is what we would call back substitution. And so that might be a term you hear thrown around. That's what we are talking about. And what we'll talk about in the next video is reduced echelon form, which is essentially just that. We have a matrix, and we might deal with like a 3 by 3 system, and we want to reduce it to something that looks a little nicer, a matrix that looks a little simpler, and then do back substitution to take it back to this, and then do this simple method to find our variables for the solution. Alright, I hope this was helpful a little bit. I'm sure that I was probably not that clear, not clearer than your professor at least, or not as clear as your professor, and I think this video went longer, but the other videos should hopefully, I'm just going to get right into the topic and do examples. Again, I can't help myself from thinking of tangents, because every time I say something I'm like, oh, I should probably explain that this is why, but I'll try to ignore that, because again, I'm thinking this course is going to be meant more for like engineers and people that aren't pure math. Well, it's not even a course, these videos. So yeah, next time we'll talk about reduced echelon form and free and leading variables, and how we can perform Gaussian elimination to solve a system. Alright.